In this lecture, we will consider some special classes of graphs. So, in the last two classes, we were looking at perfect graphs, and we in fact studied several special classes of graphs before that, because to introduce the perfect graph, we studied caudal graphs, comparability graphs, several such classes we studied. So, this is in some sense a class which will just introduce some more special classes which are not yet covered, and because I think that it is a good idea to have some awareness of these classes, these graph classes. So, when you do graph theory and so if you want to, if you are interested in doing research in graph theory, because so this is just a preliminary introduction of some of these things. So, here is one graph class which I want to introduce, which is the permutation graphs. What are permutation graphs? So, consider as permutation, say suppose 1, 2, 3, 4, 5, 6, this is a permutation, right, or you can say 1, 3, 2, 5, 6, 4, it is another permutation, or 3, 4, 5, 7, sorry 3, 4, 5, 1, 2 and 6, this is another permutation, right. So, now for each of these things, corresponding to each of these permutations, we can introduce a graph like this. Suppose you consider this permutation, namely 3, 4, 1, 2, 5. So, of 1 to 5. So, introduce some vertices 1 corresponding to each of these numbers 1, 2, 3, 4, 5. Now, what you do is whenever you have the number, say 2 pairs, if you take say I and j. So, without loss of generality, let us say I is less than j. Now, in the permutation, see their ordering. Suppose if I is equal to 1 and j is equal to 3, right. Now, this 1 and 3 comes in the reverse order in the permutation, right, it is in the wrong order. So, then we put an edge. So, for instance 1 and 2, they are in the correct order in the permutation, see here. So, therefore, we will not put an edge here. Now, 2 and 3, they are in the reverse order in the permutation, because it comes as 3, 2, so we put an edge here. So, now 1 and 4 is in the reverse order, so therefore, we put an edge here, right. And what about 2 and 4? 2 and 4 is also in the reverse order, we will put an edge here, right. And then what about 1 and 5? 1 and 5 is in the correct order, so we would not put an edge here. And what about 3 and 4? 3 and 4 is in the correct order, therefore, we will not put an edge. And 4 and 5 correct order, therefore, we won't put. This is a graph. So, you can see that 5 did not get any neighbor here, because it was in the correct order with every vertex, right, because see 5 is the biggest number, it came in the last, therefore, it is non adjacent to. So, this is the graph corresponding to this permutation. So, you can ask, suppose this permutation was just 1, 2, 3, 4, 5 like this, then what will happen? Then everything will be in the any pair, if you take, they are appearing in the correct order. Therefore, our graph will be a collection of independent, so an independent set 1, 2, 3, 4, 5, right, is not it. Now, so now you can consider the this reverse permutation, for instance 5 4 1 2 3, how will the graph corresponding to that will come? So, it will come like this 1 2 3 4 5. Here every pair, any pair if you take, they come in the reverse order. So, therefore, you will get the entire clique, right, all the edges will be there in the graph, right. Now, you can see that if all right. So, then so if you get a permutation and if you draw the graph corresponding to that, now if you reverse the permutation and draw the graph corresponding to that, then what will happen? So, then naturally if I j was in the correct order in this original permutation, when you reverse it, it will become in the wrong order, therefore, then the edge will appear, right. Or for instance, if I j was in the wrong order in the original permutation, when you reverse, they will become in the reverse order and therefore wrong right order, and then therefore, the edge will disappear. So, it will correspond to. So, when you take a permutation and draw it graph, and then you take the reverse of the permutation and draw another graph. So, these two graphs will be complements of each other, right. So, what is then we have this notion of permutation graphs. So, the question is, what is a permutation graph? So, a permutation graph is a graph which is isomorphic to some g of pi, where so g of pi for some permutation pi. What is g of pi? G of pi is the graph corresponding to that permutation. So, in other words, the issue is to get the, so we have to demonstrate some permutation. So, if you want to show that this graph is a permutation graph, if you want to demonstrate a permutation and then show the numbering on the vertices of the graph, say that okay, and then if this is the numbering, and then consider this permutation and draw the graph corresponding to that, then we have this graph should be exactly that graph. So, from that sort we are only saying that it is isomorphic to g of pi for some permutation pi, right. So, you should, because you have the option of renumbering the vertices in such a way that it becomes isomorphic to g of pi for some permutation. So, this is what is called a permutation graph. Now, so this is also known to be a perfect graph, because it is a subclass of, it is known to be a subclass of comparability graph. Is it easy to see that any permutation graph is a comparability graph? So, why is a permutation graph a comparability graph? First, let us remind what a comparability graph was. So, we had discussed it in 2-3 classes before, just before introducing the perfect graphs, we had discussed the comparability graph class. Essentially, comparability graphs correspond to a partial order, and in other words, they are the ones who can be obtained from a partial order by discarding the the directions on the edges, and so this loops and the directions on the edges. So, in other words, it captures which pairs of the set are comparable, right. And in other words, we can say that if a graph is comparability, if we can transitively orient the edges of the graph. In other words, so for instance, if you had taken this cycle, you can orient the edges of this graph like this, right. It is a transitive orientation, in the sense that whenever you see two edges in the same direction, and then this edge should be present, this third edge should be present, and the direction should be like this. That is, such an orientation is called transitive orientation. As we have seen, some graphs can be transitively oriented, for instance like this, but if it was an odd cycle, we could not have transitively oriented the graph. 1 2 3 4 5 see, yeah, for instance this graph cannot be transitively oriented. Why is it so? For instance, if you put like this, then this this cannot be, this edge is not there. So, we have to keep putting like this, right. So, we have to put like this, we have to put like this, we have to put like this. Then here this edge, so this says that you have to put it across this, but then this edge says that it should be. So, this cannot be, odd cycles cannot be transitively. So, all these things we had discussed, and now the question is, why is a permutation graph a comparability graph? Can we show that a permutation graph is a comparability graph? So, to show that, we only have to demonstrate how we can transitively orient the edges of a graph. Consider some permutation. So, now suppose it so happens that in the permutation I, so let us consider I is less than j, and so there is an edge between, these are the two vertices, I is less than j, I, j, k. Suppose you have 3 edges, right, and suppose you decide to orient these two things, then we should show that there is this edge, right, and also the direction on the edge is like this, direction on the edge is like this. So, these two things are important. Now, the question is to somehow orient the edges. So, we will decide this rule whenever so I, j is greater than I, let us put the arrow from I to j, right, from. So, therefore, so if there are two I, j, k, I j is an edge and j is an, so then I less than j less than k should be correct if you follow this rule, right. And now, the point is the fact that I less than j and there is an edge between I and j means in the permutation, suppose if you look at the permutation, j occurred in an earlier position than I, right. That is why, because that is in the wrong order in the permutation, that is why this edge is present here, right. This means this j occurred earlier than I. Now, what about jk edge? K is a bigger quantity than j, but the edge occurred means, so the k should be earlier than j. Now, what can I tell about k and I? K is bigger than I, and also there is a edge. So, the order of k and I will definitely be reversed, because j itself is earlier than I. So, k is even earlier than j. So, k is definitely earlier than I. So, therefore, k and I are in the wrong order. So, therefore, there will be an edge between them. Now, the direction is always from I to k, because we are always directing the edges from I to k. So, therefore, we have demonstrated a transitive orientation for the permutation graphs. So, therefore, the permutation graphs are transitively orientable, and then we, so therefore, we can infer that they can be they are comparable graphs, right. Now, the interesting an interesting theorem about the permutation graphs is that these permutation graphs are exactly the intersection of comparability graphs and co-comparability graphs. That means, a graph is permutation if and only if it is a comparability graph and its complement is also a comparability graph. G and G complement are comparability graphs, or in other words, if So, the other side is that if a graph is and complement and its complement, both of them are comparability graph, it has to be a permutation graph. So, we write like this, a graph G is a permutation graph if and only if G and G bar are comparability graphs. See, from all these things, so what we are saying is that suppose if I write the set of permutation graphs as P, then P is equal to the class of comparability graphs intersection the complements of that, right, co-comparability graphs. So, see, this is, or maybe this is not a correct way of replacing the essentially co-comparability graphs is what we should write, comparability, co-comparability graphs is what we should write, intersection. So, then now so we will try to prove this theorem now. So, to prove this thing, we have to prove two sides. First thing is to show that if it is a permutation graph, then it is a comparability graph and its complement is also a comparability graph. This is already we have seen a permutation graph is indeed a comparability graph. What about the complement of a permutation graph? As we have seen, a permutation graph means it has a certain permutation associated with it. That means you can identify a permutation on 1 to n such that when you construct the g of pi, the graph of that permutation, we will indeed get this particular graph, right. And now, what about reversing the permutation and taking the graph? So, of course, we will get its complement. Therefore, the complement of our graph is also a permutation, so also a permutation graph, and thus it is a comparability graph. So, what we wanted to prove is that if G is a permutation graph, this is the sequence, then G complement is also a permutation graph, and because it corresponds to the reverse permutation, and any permutation graph is a comparability graph. Therefore, both G and G complement a comparability graph. So, that is the easy part. Now, the more difficult part, suppose a graph is given G, we know that it is a comparability graph. Not only that, we know that its complement is also a comparability graph. Now, we want to show is that G is a permutation graph. Then we want to show that it is a permutation graph. In other words, we want to demonstrate a permutation associated with G such that G is the graph of that permutation. How do you do it? So, to do this thing, we first consider a transitive orientation of G. So, G is a comparability graph, therefore, it has a transitive orientation. Let us call this transitive orientation as F. What do you mean by F? It is the directed edges, because every edge in G gets a direction. So, this the collection of directed edges will be called F, because this is not this is a new entity, because essentially an edge can be given two different directions. So, we have to we cannot identify it with just the edges. So, it is we will call it F, transitive orientation. Now, the G complement is also a comparability graph, and its edges also can get a transitive orientation. Let us call it F dash, right. Let us call it F dash. So, we can even put an arrow if you want. This is the thing, this is right. Now what will happen if I take f dash union f union f dash, right. So, of course, now this the edge set of G union G complement essentially correspond to the edge set of a complete graph on n vertices, right. All the edges will come then, right. Now, what we see is f union f dash is indeed a orientation for the edges of a complete graph K n, is not it, because you have collected the edges of G and gave an orientation for each of them. It is indeed a transitive orientation. Now, G bar you took and then you gave a transitive orientation for that. This G bar contains exactly the remaining edges, and then they are all the edges of the complete graph gets an orientation now. That is what has happened when you consider the f union f dash. Now, the next point is that what can I tell about this orientation f given by f union f dash for the edges of K, the complete graph on n vertices. We claim that it is acyclic. What do I mean by acyclic? That means there will not be any directed cycles with respect to this orientation of the edges. In f union f dash, we will not have any directed cycles. This is indeed easy to prove. In fact, suppose there is a directed cycle, then what will happen? Suppose there is a directed cycle. So, then we can say that, see, suppose this is the directed cycle. We consider two cases. See, this directed cycle contains 1, 2, 3, 4, 5, 6. So, we consider the case, suppose the directed cycle contains k nodes, k strictly greater than 3. Here I drew 6 nodes. So, it can be 4, 5, 6, anything. Suppose so many edges are contained in that directed cycle. Then now you can see that. So, let's consider this thing, right, this possible 1 3, because it is a complete graph, the edge is there, right. There are two possibilities. This see, suppose there is a cycle, what we can do is we can always ask for, if there is a cycle, we can always ask for the smallest such directed cycle, right, the smallest such directed cycle. The smallest direct cycle suppose is of length more than 3, that is the case we are considering. We will contradict the fact that it is smallest, right. Why is it where is the contradiction? So, because you know this edge, because it is a complete graph, we have this edge, the direction can be either like this. If it is like this, then what will happen? Then you see we can follow this edge and then like this, and we get a smaller directed cycle. So, the fact that we took the assumption that we took the smallest directed cycle is violated here, is not correct, right. So, but then you may say that, okay, what if the direction was not like that? So, for instance, it can be the direction can be the other way, right, because it can be this way. Then you consider this directed cycle. Here this is a smaller direct cycle than this entire thing k, right. So, in either case, whether the direction is in this way or in this way, in both ways you get a smaller directed cycle. So, what can you infer? The smallest directed cycle has to be of length 3, if at all there is a cycle there. So, then you consider the smallest say directed cycle of length 3, it can be like this. Now, you can ask, there are these 3 edges, let us say A, B, C. Out of that, 2 of them should belong to F, and so at least 2 of them should belong to F. Sorry, F or F dash, one of them. It is not necessary that should be in F, or it can be in F dash also. At least 2 of them should belong to one group. Let us say without loss of generality, this A and B, because it is the same only, A and B belongs to this group, because the structure is same, because A and B, B and C, C and A, both are two edges one after the other, right. Suppose it is A and B, right, they belong to say F, F or F dash, whichever, one group. Then what happens is, because it is a transitive orientation, this F is a transitive orientation and A and B belongs to F, then A, this one, right, this edge starting from this to this edge should be there in F itself, because it is not possible to give it in the to the complement, the other side, because otherwise how can this be a transitive orientation? We gave directions like this, then this edge also should be present there, and moreover if it is present, the direction should be this way. How can you give the direction the other way, right? So therefore it is a total contradiction here, it is not possible, right. So if you have out of the three, two edges will come to the same group, which is a transitive orientation, the third one also should belong to them, and we have given it the wrong direction, because we have given the circular direction. Transitive orientation says it should be like this, right. So therefore we got a contradiction, and what was our assumption? What did we contradict? We contradict the assumption that there was a cycle. Therefore the resulting orientation F union F dash for the complete graph is indeed a cyclic orientation. Yeah. So we got an acyclic orientation for complete graph. Now what we do is, see, you recall this F was the orientation, transitive orientation corresponding to G, and F dash was the transitive orientation corresponding to G dash. Now we can suppose we have considered F bar, or maybe F bar. F bar means the same edges, edge set is same, but then whenever we directed like an edge like this in F, we will direct it in the opposite way in F dash, right. So I will reverse the directions of all the edges in F, that we get F dash, right, F bar. So this is also a transitive orientation of G, right, because it is very clear, because you see, suppose F bar is not transitive, that means that we have something like this, so some two edges like this, and we do not have this, right, or it is oriented wrongly. But then if you had reversed, then we will in F you will see this, and this should be present, right. So if this is present in F dash also it should be present, and also the F dash, the direction has to be like this. So sorry, F, the direction has to be like in F, it should reverse and give it the correct form. So it is very easy to check that if F is a transitive orientation, then F bar is also a transitive orientation. In other words, we just reversing all the directions cannot make it non-transitive. So instead of F, we could have taken F bar, and then instead of making F union F dash, we could have considered this union, that means F bar union F dash. So the same arguments will hold, and this will be also a transitive an orientation of Kn, and also a cyclic orientation of Kn, as we have proved, right, because if you again we can consider the shorter cycle and show that the shorter cycle will eventually lead to a contradiction, right. So it our inference is that F bar union F dash is also an acyclic orientation of Kn. So what is good about this acyclic orientations? So then we can order them in such a way that we get a total order corresponding to Kn, right, because if it is acyclic. So then if you do a topological sort, because it is anyway it is a total order, because all the pairs, because the complete graph we have a direction between every pair. So we will get a because it is acyclic also, we can also order them in such a way that there is it becomes a total order, right. Now what we can do is, because it is a total order, what we can do is with respect to the first one, the corresponding to F union F dash, we can create an ordering, a permutation, right. So such that so we can call it say the ordering n of, right. So, maybe we can use another another notation for that. So, h of, right. So, if corresponding to this thing we can so what we do is we go to the graph, right, the complete graph, and look at a vertex numbered I, right. So, the initially we have a number I, we are going to renumber the vertices now. So, the in such a way that we will look at the incoming edges of it with respect to this orientation, because this is incoming edges of it, right. How many edges are coming inside? Suppose there are I edges coming, then we will say make it, for instance, initially we will see a 0 edge, right, because see we claim that, see the what we can do is we claim that there is a vertex with the incoming edges equal to 0 number of edges coming inside that vertex. Why is it so? Because if every vertex is with an incoming edge, right. Then now if I track back, for instance, if I go backward through the incoming edges, where will I reach? Because every time I can go back, right, I can go back, so through an incoming edge, and then because it is a finite graph, it has to, you have to stop somewhere. So, the only way to stop is by forming a cycle. You will enter into some one of the this thing. So, therefore, because it is a cyclic, you will have to find out one vertex with no incoming edges to it. So, we can start with that vertex, we will number it 1, and then once you remove it, right, all the edges of it are going outward only, right. So, therefore, now we can see that in the remaining graph there is again a vertex with incoming degree 0, but then this vertex will be providing exactly one edge into it. Therefore, its incoming degree in the entire thing is 1. Therefore, that can be called the second vertex, and so on. So, that means there will be a vertex with I incoming edges in it, then that vertex will be called I plus 1. 0 incoming edge will be called 1 first vertex, the 1 incoming edge exactly will be called 1, 2 incoming edge will be called exactly 2, and so I incoming edge will be called the vertex I plus 1, right. So, we number the vertices like that based on that. So, similarly, we will consider the other orientation, namely f bar union f dash, and based on that also we will define a numbering. We can call this numbering as h. The vertex x will be given the corresponding name here, the vertex sorry h, this is h, the vertex h will x will be given the number of incoming edges will be the plus 1 will be the name for that. Similarly, with respect to this orientation we again make another this thing. So, for h dash of x, now the interesting thing about this h of x and h dash of x is that if you take any edge of the original graph G, if you consider any edge of the original graph G, so what is interesting is in this first one, if the direction is like this, in the second one the direction will be reversed, it will be like this, right. So, therefore, if with respect to h this got a lower number and this got a higher number, with respect to h dash this will get a lower number and this will get a higher number. So, essentially they will reverse their roles. In other words, what we can say is that for if x y is an edge of G, if x y is an edge of G, now h of x minus h of y into h dash of x minus h dash of y will be less than 0. So, that is what, right. So, that product will be negative, or in other words, so we do not have to worry too much about it. So, essentially what we are trying to tell is whenever x and y, if x is greater than y in one of them, the values corresponding to x and y is such that h of x is greater and than h of y in the first one, then the order will reverse in the other one. So, so therefore, when you just put h of x minus h of y into h dash of x minus h of y, h dash of y, we will get a negative value, right. So, now we will construct the permutation like this. So, we will take a vertex I, right, we will take a vertex I, and this vertex in the first with respect to h of x, maybe we will find some x such that h of x is I somewhere in the, so that permutation I will appear somewhere, right, in that permutation I will. So, this is the position x, right, x position I has appeared. Now, what you do is, so we will consider in the corresponding position what is there here, right. Now, that position will be made. So, we will take this value and in the corresponding position, right, we will place I. That means, pi inverse of I will be made h dash of x. If h of x is equal to I, then we will make pi inverse of pi I inverse is equal to h dash of x. The position number corresponding to I will be made h dash of x. Now, we know that h of x, for whenever there is an edge, h of x minus h of I into h dash of x minus h dash of y is negative, right. So, it is less than 0. So, but then this is essentially our, so suppose I j is an edge, then this is essentially some x and y corresponding to, so this I is, this is I, this is j, right, and then this is what, this is pi inverse of I minus pi inverse of j, right, because this is by decision. So, this will be less than 0. This is, we are making use of this property. So, what does this later inequality means? This later inequality means if I is smaller than j, then the positions, corresponding positions will be reverse, right. I will be in a, if I is a smaller number than j, then pi I should be a greater number than pi j, pi I inverse should be a greater number than pi j inverse. So, therefore, they will appear in the permutation in the wrong order, in the corresponding permutation. Okay, we also have to consider the edge set, suppose there is no edge between. So, we consider when there is an edge here, suppose there was no edge here. If there was no edge here, then we know both in both cases, if this also in both the orientations, we will get the same direction for that, the corresponding pair, right, the edge, because we are not changing, we are only changing. So, we had once f union f dash, the other thing was f bar union f dash, right. In this thing, suppose the pair was like this, in this thing the pair, so for instance x y is a known edge, right. So, then that belongs to f dash only. So, we gave this direction, and then here also x y will belong to this f dash, we are not changing it. So, it will be the same orientation. So, if the values assigned to this h of x, if it is less than h of y here, so h dash of x will be less than h dash of y also here, because the orientation, the directions are same. So, therefore, there they will not, whenever there is known edge, this h of x, so then see h of x minus h of y, right, into h dash of x minus h dash of y will be greater than 0, right, because they will be positive, either they are both positive or both negative, therefore they are positive. Therefore, it will we can say that this property of being negative will happen, that product being negative will happen only when this x y is an edge. If x y is not an edge, that will not reverse. So, we have described now how a permutation can be constructed from the graph. So, we will summarize the idea of the proof. So, we wanted to show that if G and G complement both have transitive orientations, then G is a permutation graph. So, what we did is we considered the transitive orientations f and f dash of G and G complement. If f is a transitive orientation, the f bar which is obtained by reversing all the directions is also a transitive orientation of G. So, then we considered two kinds of orientations of the complete graph, mainly f f dash and then f bar f dash. This was the crucial thing, and both are acyclic. This is what we proved, both are acyclic, and acyclic means we have a total ordering there, and then we considered a numbering h of x from based on this, and considered a numbering h dash of x based on this, right. This h of x, so numbering was just that you counted the incoming edges for a vertex and plus 1 was given as its number, right. That vertex was labeled with that number, that is h of x, that is h dash of x. And this h of x and h dash of x will have the property that this, if you consider this product h of x minus h of y into for two vertices x and y, suppose if you had considered this product, means when you minus this h of x minus h of y and h dash of x minus, this is less than 0 if and only if x and y are adjacent. If they are adjacent, this has to be in two different, because of we reverse the edge directions in both the cases. So, one will be if this is positive, this has to become negative, and vice versa. Similarly, so if there is no edge, then both will have the same parity. Therefore, if this is negative, this also will be negative. This is positive, this is also negative positive. Therefore, that will be positive. So, then based on this h of x and h of y, we constructed a permutation. How did we do that? We just considered for every vertex I, for every I we looked at for which x is h of x equal to I, right, and then we placed I in the permutation in the which position, by inverse I is equal to h dash of x. In we looked at the permutation h dash of x in that x position, whatever values you in that was the position number corresponding to I, and then you see because of we immediately get this this thing that pi I inverse minus pi j inverse into I minus j is less than 0 if and only if I j is an edge, right. So, therefore, this means that the whenever I j is an edge, I and j come in the reverse order in the corresponding permutation. Therefore, it is a permutation graph. So, this is, so we conclude the permutation graphs with this thing, right. Now, so we will consider some other graph classes also. So, this is maybe I will just give you a quick overview of things. So, one graph class we want to consider is the some see we will say that generalization of interval graph. Interval graphs are very important class. Therefore, people have tried to generalize in various ways. So, in this 15 minutes what I will do is to introduce a concept which tries to generalize the interval graphs. So, because again this is a, see, as we know, interval graphs are the intersection graphs of intervals on the real line, right. So, this is because we saw that each vertex is associated an interval on the real line. Whenever two vertices are adjacent, we put an edge between them, otherwise we do not, we put an edge between them. That is the meaning of intersection graph of intervals of on the real line. Now, suppose you want to, instead of considering intervals on the real line, what if I want to consider rectangles on the plane. For instance, I want to associate with each vertex a rectangle, axis parallel rectangle on the plane, such that two axis parallel rectangles intersect if and only if they those two vertices are adjacent. This is called a rectangle graph. In fact, if a graph can be represented like this, it is called a rectangle graph. Interesting. For instance, if you take a cycle, you can represent it like this, 5 cycles. See, so this is a 5 cycle. So, what you do, this is 1, this is 2, this is 3, this is 4, this is 5. So, corresponding to each vertex, we are placing an axis parallel rectangle, and then we are allowing them to intersect only when there is an edge between this. For instance, here 1 and 2, here is an intersection between this thing, but because 1 and 2 are adjacent with each other, right. And similarly, 2 and 3 are made to intersect because they have an intersection between them. Now, you can see that this is a kind of generalization of interval graphs in the following sense. So, because this interval graphs are intervals on one dimension, because these rectangles, for instance, if you take a rectangle, it can be seen that an interval is growing. For instance, it's a Cartesian product of two intervals. For instance, this is one interval, if you consider this interval. So, it is a Cartesian product of intervals. So, this can be considered as a two dimensional interval, right, because so if you give this interval and this interval, they are Cartesian product. So, this is the corresponding interval, right. So, it is a, so then while just like interval graphs of the intersection graphs of one dimensional intervals, these are the intersection graphs of two dimensional intervals, right. Now, you can ask this question. So, so we know that there are interval graphs which cannot be represented as the intersection graph of one dimensional intervals. Similarly, there are graphs which cannot be represented as the intersection graphs of two dimensional intervals. Can you quickly find out one graph which cannot be represented as the intersection graph of two dimensional intervals? So, this is one interesting question. So, you can see like this. To study this thing, and we need some kind of model. So, suppose you consider a rectangle graph. This is a rectangle graph, right. Now, if you are given a rectangle representation of the given graph, that means a vertex is associated with some rectangle. So, we draw a rectangle corresponding to any vertex, and then and whenever they are adjacent, we have to make the rectangles intersect. Now, we can create two interval graphs from this thing. So, what we do is we project these rectangles to the corresponding axes. So, this is one, this is one, the corresponding to this, right. This is the third interval. So, So, if you take the projections of the for each rectangle into the corresponding axes, then what will happen is we will get an interval graph corresponding to that. Suppose this is a vertex u, when you take the projection you will get an interval corresponding to u, right, I u. Similarly, when I take the projection of this thing, you will get an interval corresponding to v I v, we can say, right. Now, you can see that whenever these two boxes here, rectangles here intersect, the corresponding projections also should intersect, right. So, therefore, whenever there is an edge in this rectangle graph, in the interval graph you obtained by taking the projections also should have the edge. So, but when there are no edges between them, for instance between this box and this box there is no intersection, therefore, the corresponding vertices will not have an edge between them. Now, if you take the projection, then also it is not guaranteed that then it is not guaranteed that they are again non intersecting, because these two projections are intersecting. So, what we can say is that the interval graph we obtain by taking the projections of these rectangles is indeed a super graph of the given rectangle graph. It is not actually the exact graph. There can be some extra edges, but all the edges which are present should be always present, but some extra edges may come, therefore, it is only a super graph. Similarly, if you had taken the projection to the y axis, you would have got another super graph. So, the interesting thing, so for instance, suppose G1 is the interval super graph obtained by taking projections to x axis, and G2 is the interval supergraph obtained by taking projections to y axis. Then we can easily see that if I had taken G1 and G2 both have the same vertex set, because the corresponding to each box we took a projection to x as well as we took a projection to y, right. So, therefore, in both cases we see that the there is a projection corresponding to one vertex, there is a box corresponding to one vertex, and therefore, when you project there is a projection corresponding to. So, it is on the same vertex set, G1 vertex set of G1 equal to vertex set of G2 equal to vertex set of G. But on the other hand, if you consider the edge sets, we can easily see that the edge set of G is equal to the intersection of the edge set of G1 and the edge set of G2. To see this thing, we have already observed that EG1 and EG2 both are supersets of EG, right, superset of EG, isn't it. So, because whenever there is an intersection, we anyway get that. Now, if some edge x y is missing in G, suppose there is this x y which is not there in EG, then that means two rectangles corresponding to x and y do not intersect, it will be like this. So, it can be some x and it can be some y, right, it can be something like this. Now, it is possible that in one of the axes their projections intersect, but it is not possible that in both the axes their projections intersect. In both axes if their projections intersect, then the rectangles themselves have to intersect, because the rectangles are the Cartesian product of these projects. It is very easy to see that if there is a common point in both the projections, then their Cartesian product have to intersect. Therefore, we can easily see that in either G1 or G2 will be such that either G1 or G2 will be such that where this edge which is not there in EG will not be there in EG1 or in one of those graphs. That is why this E of G becomes the intersection of E of G1 and E of G2. Now, why did we tell this thing? You suppose you have if a graph can be drawn on the 2-dimensional plane as the axis parallel intersection graph of axis parallel rectangles, then we can find out two interval graphs I1 and I2 such that G is equal to I1 intersection I2. When I say I1 intersection I2, the vertex set is same for all the graphs, the edge sets intersection edge set of G will be the intersection of edge set of G. Now, we claim that if you consider this small graph, so you take this graph, now this is missing, so this connection is there, and this is missing, this connection is there, this connection is there, this is missing. Now, we claim that if you consider this graph, this cannot have a representation in 2-dimensional plane. So, this is because these 3 edges should be missing in I1 or I2, right. Each one of them should be missing in one of them. Now, pigeonhole principle says that there are 3 of them, there are 2 interval graphs. Now, 2 of them should be missing in one of the interval graphs. Suppose without loss of generality, this and this edge becomes missing in I1. Then what will happen? Then you see that there is a 4 cycle like this, which will because this all the edges which are there here should be in I1 also, because there I1 is a super graph, and then these 2 edges are missing, that means there is induced 4 cycle, which is a contradiction. Therefore, 2 interval graphs cannot give G as an intersection. So, thank you. We will stop the class with this.